Yeah. All right. So number 36, somebody or a couple of people, I don't care. Y'all tag me. I mean, it works for me. Let's put that one on the board. Let me erase everything that I want to erase first. All right. Number 36. Usually try to hop on a freight train traveling at a constant speed of 5 meters per second. Just as the empty boxcar passes in, the future starts to rest and accelerates at 1.4. There's a maximum speed of 6, which he then maintains. How long does it take to catch up to the empty boxcar? What is the distance traveled to reach the boxcar? I think two ways to do this. One is kinematic equation, and one might be graphically. Yep, y'all go ahead. I don't care. Pick one.
So we know the starting, like, should I just work it out on the board or like?
Yeah, however you want to do it.
So
You got the floor.
starting velocity of the fugitive, which is from rest, so it's 0. And then we have the acceleration. 1.4 meters per second squared. Then we know he has a final velocity of 6 meters per second. So while he's accelerating, the train's already moving. So I think what we need to find here is time. Time one. So if we take our first kinematic equation, and we solve it for time, we get velocity minus initial velocity over A. And we plug in everything. Gives us what initial time over. So while the fugitive is accelerating, the train's already moving at 5 meters per second times this is time 1. And then we need to find time 2. So like if both of them are moving at their like constant speed, how long does it take for them to like intercept or for the fugitive to overtake? So we're gonna have the same velocity for the train times second time variable. Then on the right we're gonna have their fugitive. So if we plug in our time 1 right here, we're gonna get 21.45 meters. Then if we subtract this over here, we're gonna end up with 1.0 meters per second. Times 2. Divide those, and I get time 2 equals 21.45 seconds. So if we add up time 1 and time 2, that gives us total time to reach an empty box score. Total time 5.74 seconds. And then I think our distance would be either side of the this one. Delta X is 128.7 meters. That is my educated. I guess, but I attend something wrong.
Okay, somehow your numbers are almost twice as big, so you missed a divide by 2 somewhere. It's my first guess. The answer is 13 seconds and 64 meters. So you got 26 seconds and 128 meters. So somewhere you've got double the right answers. So let's think about this just a minute.
You said 64 meters?
Yeah.
And then 13 seconds.
Yeah, so you're twice as big as okay. Let's think here. You got walk me through the 5 plus T1 plus 5 plus T2 equals 6 T2 again.
So, while the fugitive is accelerating, the train's already moving for that amount of time it takes for him to accelerate up to 6. And then it moves the additional amount of time at that same time. I'm not
Okay.
completely sure that's just like.
All right, let's think of it. So we would like to know the time T, look, part A, right, is T when their X's are the same, right? We're going to call where they start at X0 equal to 0. Okay, let's think of it this way. So if we have fugitive both start at the same spot, right? We'll call that 0 for simplicity's sake, right? We get to pick our origin, right? If it's 0, then that makes math easy, takes terms out of the equation. They're both going to, we want to know when they end up in the same spot. Okay, which is their final displacement. Fugitive is accelerating, right? So he has an acceleration of 1.4 meters per second squared. The train is not, correct? Constant. So it has an A of 0. All right, this had an initial velocity of 0. The final velocity of, does it tell us? 6. This has an initial velocity, final velocity that is the same. Of 5. 0 acceleration, existing numbers have to be the same. Okay. So we don't know the value of X, but we do know that these two are equal to each other, right? We want to that, we also know that those two things are equal to each other. So the time it takes the fugitive to get to this position and the time it takes the train to get to this position are the same time because of the same position. All right, that makes sense? So, if we had an equation that had time and position, use that equation for each object. All right? And then we can set them equal to each other because we got things in the same, right? So, final position of the fugitive is his initial position plus, let's try to write it somewhere, plus the initial velocity times the time plus half of his acceleration times the time squared. Final position of the train is equal to its initial position plus its initial velocity times time plus half its acceleration times time. Okay. Now, the initial position of both of these objects is 0, right? So that term goes away. So anytime you can take some zeros and do real stuff, okay, that goes away. The initial velocity of the fugitive is 0. So that means this whole term goes away. Okay? I follow that? The acceleration of the train is 0. So that makes that whole term go away. Things are starting to get a little simpler, right? Okay. If their final positions are the same, then that means this equation is equal to this equation. So we can put 1/2 the acceleration of the fugitive times d squared equals the initial velocity of the train times t. Let's label some things here before we move on. This is the acceleration of the fugitive. This is the initial velocity of the train. Okay. All right, so now, divide both sides by t. That'll go away. With those go away. So up here, I've got 1/2 acceleration of the fugitive times t equals the initial velocity of the train. I hope this is right. So the time is 2 initial velocity of the train divided by the acceleration of the fugitive. That's 2 times 5 meters per second over 1.4 meters per second squared. I hope that's 13. 10 divided by 1.4.
It's 7.14.
I did something wrong too. Okay. thought I was on the side. Still think that ain't what I'm missing. He started from rest, right? From rest. Accelerates at 1.4. So his displacement, you have his acceleration times his time squared. Train's displacement should be his velocity times 9 because he's not accelerating. They cover the same amount of ground. I need something. Okay, let's go to the answer key. Both got it wrong. You got twice as much. I got almost half as much. Okay, let's see. So we're leaving out the 6 for some reason in my solution, the final velocity of 6. Okay.
Maybe like for the fugitive, we have to add on like a velocity times t term for like when it's just moving constant at 6.
Okay, here's what we're missing. Okay, yeah. All right, so here we go. This says the first possibility to consider is, can the fugitive catch the boxcar before he reaches his maximum speed? So our equation, the way I got this set up over here, it assumes that he keeps accelerating on and on and on, right? Which is not humanly possible, right? At some point you reach a maximum speed. Okay, so they do the same math I did, and they get an answer of 7.1. Okay, all right, but they're saying that okay, the first thing they did is they figured out how long it takes the fugitive to accelerate to 6 meters per second. Okay. So they took the kinematic equation number 1. Said, how long does it take him to get 6 meters per second? What's that come out? What something? 1, 2. What, how much?
Good morning, teachers and students. Could I please have your attention for a quick announcement? This is a reminder that tomorrow morning, the freshmen, sophomores, and juniors, and those seniors that elect to, will take ACT practice test number 1. This is a very important baseline test. 7th and 8th graders will be testing reading and math through IXL. So we need to be rested and prepared for that. In preparation, during advisement this morning, I would like all students to make sure they have their Chromebook so that we can do a practice login to Mastery Prep. and IXL to make sure there are no technological issues. So when we get to advisement, teachers, if you will, have your students log in to their Mastery Prep account or IXL. I am sending an email to all faculty, staff, and student email accounts with a reminder of the step-by-step process of how to log in, so we want to make sure we don't have any issues. That is our goal for advisement this morning. Thank you.
Okay, so the problem with what I did was that assumed he kept accelerating. He only accelerates for 4.29 seconds, right? So how's he ever going to catch the train? Well, because his velocity is faster than the train at that point. Okay, so he will catch the train. How much time have I got, by the way? 3 minutes? Great. I need about 30, so it's good. Here, let me put this on the screen so y'all can see what I'm looking at. What in the world? Come on. There we go. Okay.
Teachers and students, again, please pardon this interruption. One more thing to note for your planning purposes. We will likely do a practice run reporting to our Mastery Prep locations and IXL locations before the school day is out, just to make sure that everyone gets to the right place and that the rosters are correct. So be prepared for that, likely after lunch. Thank you.
So we're just going to. Now I got less than what? I got a minute, 2 minutes. Okay, let's just do this. We'll finish this Wednesday. Okay. Also Wednesday, we're going to preview some labs. We're going to do the rest of the week. Okay. So tomorrow's ACT. We'll finish this question Wednesday. Please ponder it yourself if you'd like to. If you want to take a picture of that or something, it'd be cool. I could print it off possibly if I can find it right, but I don't know what page it is. Anyway, do that. Okay. Keep pondering number 36. It's a little complicated, obviously. Wednesday, practice out of the textbook. I'm going to pick a couple of those level 2 questions from that problem set. Ones that are level 2, I'll pick a couple of those. We'll take a little quiz Wednesday, and then go over some labs that we'll do Thursday and Friday. Okay. That work? All right. Sorry for the bell ringing before we finish this and not being here tomorrow, but there's nothing we can do about that. So we will finish it Wednesday and go from there.